Good morning and welcome everyone to today's lecture. And in today's lecture, what we will be doing is we'll be venturing into the most important aspect of this particular chapter, which is known as thermodynamics. Now, when I use the term thermodynamics basically refers to the entire branch, but what we are using here for is we'll be dealing with thermodynamic processes. I hope you have got the sheet. Did you get the sheet for thermodynamics?
Sir.
Yes, sir or no, sir?
Yes, sir.
Yes, sir. So we open that sheet and we have a look into that sheet and tell me what all things are we going to study in this particular topic. Tell me what we are going to do in this chapter. Give me a bird's eye view of what are you expecting that we will be covering in this particular chapter. Remember, there is a reason that I have done thermodynamics and not other chapters, because thermodynamics, this particular chapter, is basically common in both physics and chemistry. So I thought that we should be doing this. So what all things are we going to do here? Any idea? Huh?
Conduction, radiation.
Radiation? See the radiation? No, radiation will do. Yes, we'll do, but not now. We'll be doing it after some time. We'll start with slot, float, and slot. What is slot? What is float? And what is slot? Any idea? Slot is zeroth law of thermodynamics. This is known as the zeroth law of thermodynamics. Have you heard about zeroth law of thermodynamics? Slot is zeroth law of thermodynamics. It tells us about the concept of temperature. If you know or you don't know the law, it tells us that if body A and B are in thermal equilibrium, A and B are in thermal equilibrium. What do you mean by thermal equilibrium? Any idea what do you mean by thermal equilibrium? Thermal equilibrium means the body are at same temperature. So if I have three bodies, A, B, and C, body A and body B are in thermal equilibrium. Body B and body C are also in thermal equilibrium. Then this law states that body A and body C are also in thermal equilibrium. Do we understand this?
Yes, sir.
Thermal equilibrium means they are at the same temperature. When two bodies are at the same temperature, we call it thermal equilibrium.
Sir,
That is zeroth law of thermodynamics. Yes, what happened?
we didn't get sheet, sir, of thermodynamics.
You didn't get sheet of thermodynamics? Well, I've already sent them to you. Maybe you will get it. I'm sorry if you did not get it. It's already sent. I'll just check. I've already sent it. I hope I have not made a mistake or that I sent you two sheets, but I did not send you the third sheet. Normally that mistake doesn't happen. Should not have happened. So I'll check. Check, 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 check. Check, 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 check. And I already sent. I have sent you 1, 2, 3, 4, 5, 6 sheets. 6 different sheets. 3 for theory and 3 for exercises. How many did you get? You should have got 3 sheets at least. 6 sheets. 3 for theory and 3 for exercises. If you got less, that means you did not get the entire lot. And just ask your people over there to give you the thermodynamics wala sheet. Okay? Shall we move ahead? Float is known as the first law of thermodynamics and slot is known as the second law of thermodynamics. Now we'll go through all these laws. This is just an introduction. The zeroth law of thermodynamics deals with the concept of temperature. The first law of thermodynamics deals with energy conservation. It is nothing but law of conservation of energy. And the second law of thermodynamics tells us how or in what direction heat can flow. First law does not tell us in which direction heat flows. Second law tells us in what direction heat flows. You might have heard about heat engine. It converts heat into mechanical work. Steam engine is the heat engine. Your car ka engine, your car that runs on petrol or diesel, it is also a heat engine. It converts heat into mechanical work. I hope you all understand this. Can I move forward? To understand this, please raise your hands. So this is a brief introduction which all of us basically know or we must have heard about it. Now, we must understand that this chapter deals with heat, work, internal energy sort of things, and therefore we would understand how they are related to each other, and that is how they are related to each other. Heat is a form of energy. Energy is the capacity to do work. So, heat and work are related to each other. Work can be converted into heat. Heat can be converted into work. Yes or no? We understand this.
Yes, sir.
But again, 100% conversion is not possible. It is not possible that you give someone 36 or 30 joules of heat and he does 30 joules of work. That is not possible. Do we arrange that? Do we understand this? So heat can be converted into work. Work can be converted into heat. But 100% conversion may not be possible. Do we understand this?
Yes, sir.
Heat and work, they are both form of energy. The first conversion was given by Ramford. The mathematical expression was given by Joule, that work and heat are related to each other. We know this. Yes or no? Either we know it or we don't know it. We know this?
Sir.
Yes, sir. And work can be converted into heat. Heat can be converted into work. And we have this this constant J, mechanical equivalent of heat. Have you seen this constant mechanical equivalent of heat? W is equal to JH, where W is in joules and heat is in calories. Do we understand this? Yes or no?
Yes, sir.
1 calorie is equivalent to 4.2 joules of energy or work. Should not say work. 1 calorie of heat energy is equal to 4.2 joules of heat energy. 1 calorie is more than 1 joule. 1 joule is 0.24 calorie. 1 calorie is 4.2 joules. You must be knowing this. Yes or no? If you don't know this, I will give you a minute to note it down. Please note it down. I hope you will get the sheet by today. Ask that office people to give you that. Okay? You can do that for me? Are no one is saying anything? Is everyone noting it down?
Yes, sir.
Good, sir. Why is the camera moving, sir? I mean, when you have to go that you move the cameras or what? So that I can't see. I can see everything. I have a all-seeing eye that can see everything. Don't worry. You must have heard God is omnipotent and omnipresent. I am also like that. I am also present there. I am God. How can God be omnipotent and omnipresent? Well, he lives in a higher dimension. I'll tell you about all this higher dimension when you clear your NEET. Are you done with that? Shall I move forward?
Yes, sir. Done.
Then we see this conversion of work into heat. Work can be converted into heat. Heat can be converted into work. To convert work into heat, you divide it by joule. To convert heat into work, you multiply it by joule. J, mechanical equivalent. Do we understand this?
Yes, sir.
If potential energy is converted into heat, remember, whenever I am dividing it by joules, I am basically converting joules into calories. Do we understand this?
Yes, sir.
Whenever I am multiplying it by joules or J, I am converting calories into joules. Normally, a question, if it comes, it may not be in calories, it may be in joules. One part may be in calories, the other part may be in joules. So don't get confused by this J. To convert calories into joule, multiply by J. If you understand that, if you remember that, you can do the other thing correctly. Do we understand this? Kinetic energy is half mv square. If I have to convert it into calories, I will divide it by joules. And that will be equal to m into s into delta theta. Have you seen this formula, ms delta theta?
Yes, sir.
M stands for, in this formula, M stands for what? M stands for what? M stands for the mass of the body. Will we remember this?
Yes, sir.
What does delta theta stand for? It stands for change in temperature. Will we remember this?
Yes, sir.
S is known as the specific heat. Will you remember this?
Yes, sir.
Please note it down. I will give you a minute to note it down. If you have rotational kinetic energy half I omega square, do we know rotational kinetic energy? Yes or no?
Yes, sir.
Dividing it by joules, J converts it into calories. That will be equal to ms delta theta. There might be a question that comes to you. A body is falling from some height. A body is falling from some height. How much energy or heat energy is lost? mgh will be the total energy divided by joule J. You will get energy in calories, heat energy in calories. And if you equate it to ms into delta theta, you will find out how much the temperature of the body will change. Do we understand this?
Yes, sir. Understood.
We will do one question and that will make the thing very clear. A minute to note this down.
Done, sir.
Done, sir. Well done, sir. Then I will move fatafat ahead without losing any time. And just to make a sense of what I was babbling, this is a question that might make you understand what I was talking about. And this is the question. If the Earth suddenly stops its rotation, oh, I hope that day doesn't come in our lifetime. What will be the rise in temperature? What will be the rise in temperature if Earth suddenly stops rotating? Oh, that would be disastrous day. I am sure. If you don't die by rise in temperature, we will die by many more things. Remember, we are rotating at an angular speed with which the Earth rotates. If it suddenly stops, my God, you will not be able to see anything. You will not be able to even send a SOS message. Who will you send the SOS message to? Everyone will stop rotating. How do you do this? Any idea?
No, sir.
No one has any idea. So the concept is pretty simple. Earth is rotating. It has what type of energy? It has rotational kinetic energy, half I omega square, yes or no?
Yes, sir.
Where I stands for the moment of inertia of Earth, omega stands for the angular velocity of Earth. The values are not given, so I will use it as I and omega. We understand this? Can I have some raised hands? I divide it by J because I want to convert joules into calories. That must be equal to m, where m stands for mass of the earth, S stands for the specific heat capacity of earth, and delta theta stands for the change in temperature. Now earth is a sphere, the solid sphere. Sphere is always solid. The moment of inertia is 2 by 5 mr square. Do you remember moment of inertia of a solid sphere?
Yes, sir.
We put the values here. From here you can find out the value of delta theta. Delta theta is the change in temperature of earth, and this is the result that you will get. I have not done anything here. I have just written the formula half I omega square is equal to ms delta theta. I divided by J because one thing is in joule, other thing is in calories. Moment of inertia I is 2 by 5 ms square. I put the values and I get the answer. I'll give you a minute to note this down. Anyone has any doubts on this? Please raise it now. If no one has a doubt, a minute, and after this minute, one more question will come. And I hope you can do it.
Done, sir.
Done, sir. Well done, sir. This is the next question, sir. Waterfalls. Water, money, waterfall. This is a waterfall. Water is falling from a waterfall from a height of 50 meters. Oh, very high waterfall. 1/3 of its mechanical energy is converted into heat. What is the rise in temperature? Remember, 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 remember. You must know what is the specific heat of water. What is the specific heat of water? Specific heat of water is 1 calorie per gram per degree Celsius. So it takes 1 calorie of heat to raise the temperature of water 1 gram of water by 1 degree Celsius. We will be doing this specific heat in the chapter known as calorimetry. Don't worry. Right now, just take it as a formula and we will discuss this formula later on. Is anyone there in the class? Can I have some reason that we are there in the class and we understand what is being talked about here? So now water is falling from a height of 50 meters. When it comes down, 1/3 of its mechanical energy is converted into heat. Remember, the entire mechanical energy cannot be converted into heat. Some part is always lost. How much is the rise in temperature of water? I'll give you a minute to solve this. I've told you specific heat of water is 1 calorie per gram. Normally, if this question comes, they would give you this value. Even if this value is not given, you should be able to solve it with your knowledge. A minute, you will get. Any success? Did you get? How will you get the rise in temperature of water? Well, don't worry if you did not get it. The question is pretty straightforward, and here is how you need to solve it. It's falling from a height, so the loss in gravitational potential energy is mgh. Do we understand this, everyone? 1/3 of its energy, as you can see, 1/3 of its energy. So 1/3 of this is converted into heat. Now this is in joules. So I divide it by J, which is the mechanical equivalent of heat. That must be equal to ms into delta theta, m standing for mass, s standing for specific heat into delta theta. Yes or no? Do we understand this?
Yes, sir.
We just multiply, divide, and we get the answer. M is gone, M is gone. What is the value of G? Tell me, bacha. G is 10. Do we understand this?
Yes, sir.
Height is 50. Do we understand this?
Yes, sir.
3 is 3. Do we understand this? And joule is joule. Do we understand this?
Yes, sir.
Here M is mass. Delta theta is change in temperature. But I had given you that the specific heat is 1 calorie per gram, but they have used 1000. Why they have used 1000? Because everything has to be in SI unit. Therefore, in place of kg, they will, in place of gram, they have kg, and therefore the answer becomes 1000 calorie per kg. Do we understand this?
Yes, sir.
And that is why you do the calculation. The change in temperature, as you can see, is coming as 0.04 degrees Celsius. Another example where when something is falling, it is losing energy. 1/3 of its energy is converted into heat. And from that heat, we have found out how much will be the rise in temperature. This comes from a chapter known as calorimetry. We will do a very short recap or very short discussion on calorimetry so that we understand and we should be able to solve questions of this nature. I'll give you a minute. I will give you a minute to note this thing down. Do we understand the formula that is given here? M into S into delta theta. Do we understand this formula? Yes or no?
Yes, sir.
M standing for mass, S standing for specific heat, and delta theta standing for change in temperature. Now to give you another example. What is calorie? I told you how much is 1 calorie. Heat required. Oops. Heat required for 1 degree rise of temperature of water from 14.5. So if water is at 14.5 degrees Celsius, you increase the temperature to 15.5. You have 1 gram of water. So in a beaker, you take 1 gram of water. You heat it up from 14.5 to 15.5 degrees Celsius. Whatever heat is required, that is known as 1 calorie. That is the definition of 1 calorie. Do you know this definition, bacha? If you don't know this, please note this down because this is important that you know it. Please let me know once you have noted it down.
Completed, sir.
Completed, sir? Then this is one diagram which will come as a straightforward question in your exam. This is known as anomalous expansion. It's written as expression. It is not expression. It is anomalous expansion of water. What is this anomalous expansion of water? Now, what we have seen in day-to-day life, if you heat something up, if you heat water up, what happens? It expands, yes or no?
Yes, sir.
On heating anything, especially water or anything, it expands. I'm increasing the temperature of water. Temperature of the water, theta is increased. The volume of water increases. Do we understand it from here point on the blue hand side, on the right hand side, blue? When I'm increasing the temperature of water, the volume of water increases. That happens when the temperature of water is more than 4 degrees Celsius. But there is a small thing here. When the temperature of water is between what and what? When the temperature of water is in the red zone, and the red zone is from 0 degrees Celsius to 4 degrees Celsius, in this zone what happens, when you increase the temperature of water from 0 to 4, the volume of water decreases. Do we see this? Do we see this decrease in volume of water?
Yes, sir.
The volume should not have decreased. The volume should have increased, but the volume decreases. Therefore, water has the least volume at 4 degrees Celsius, or water has maximum density at 4 degrees Celsius. Do we see this? I will do what? I will enhance the graph so that you can see the graph correctly and you can draw it correctly. Here it comes on full screen. I hope you can see this. Anyone can see this graph? From 0 to 4 degrees Celsius in the red zone, the volume of water should have increased, but it is decreasing. This is known as anomalous expansion of water, not expression. Anomalous expansion of water. After 4 degrees Celsius, water behaves normally. When I increase temperature, the volume of water increases. Have you drawn this diagram?
Done, sir.
Done, sir. Then there is a sister diagram of this. And the sister diagram of this gives us the density of water against the temperature of water. Water has maximum density at 4 degrees Celsius. If you make the temperature more than 4 degrees Celsius, it decreases. If you make the temperature less than 4 degrees Celsius, it also decreases. Do we understand this?
Yes, sir.
This is known as anomalous expansion of water. Will you remember this, bacha?
Definitely, sir.
Don't forget this. I'll give you a minute to draw this diagram, and then we shall move ahead in our lives. 1 minute, a minute to minute.
Done, sir.
Done, sir? Then, sir, these important points, sir, which are coming to you on your screen right now. Between 0 degrees Celsius to 4 degrees Celsius, mass of the water cannot change the mass of water, but the volume of water will decrease. Volume of water will decrease. CV of water is greater than CP. You may not know this. This is irrelevant. Point number A and point number B must be known to you. At 4 degrees Celsius, volume is minimum, density is maximum, surface tension is maximum, capillary height is minimum, because they all depend on the density of water. Between 4.5 to 15.5 degrees Celsius, density of water is constant. So 1 calorie is defined in this range. These are the important points that you must remember. Can you note them down for me? I'll give you a minute to note it down. We've already discussed this. This is just a confirmation of what we have done.
Done, sir.
Okay, sir. Then we will move ahead, sir. Now, what we have seen up till now is the formula that heat given or heat taken by anyone is equal to m into s into delta theta. Yes or no?
Yes, sir.
Now, this happens when the temperature of the body changes. You give heat to a body, the temperature increases. You extract heat from a body, temperature decreases. Do we understand this?
Yes, sir.
In case of temperature change, the formula for heat that we use, heat given or heat taken out, is ms into delta theta. Do we understand this?
Yes, sir.
But there is one more process where when you give heat to a body, the temperature of the body does not change. In fact, the phase or the state of the body changes. For example, when water is at its melting point, when ice is at its melting point, if you heat it up, that ice, solid water, will convert into liquid. Do we understand this?
Yes, sir.
If water is at 100 degrees Celsius, you give it heat, it will vaporize or convert into vapor. Yes or no? In all these processes, if you do ulta of this, if you have water at 0 degrees Celsius and you freeze it, it will become ice. If you have water vapor at 100 degrees Celsius, you condense it, you will get water at 100 degrees Celsius. In all these cases, on the left hand side, we will give heat to water, which is taken as positive. On the right hand side, we have taken heat from water, which is taken as negative. Do we understand this?
Yes, sir.
Now, this process is different from the process where the temperature of the water changes, because in that process, temperature of water is changing. But in all these processes, process number 1, 2, or 3, or the reverse of this process 1, 2, and 3, the temperature of the body is not changing, but the phase of the body is changing. All these phase conversion processes are isothermal. I hope you know what is isothermal. Same temperature. And isobaric, same pressure. We will do all these processes in this class today or tomorrow. Right now, you just notice down what I have given. Do we understand this? So there are two types of processes here we are talking. There are two types of processes that we are talking about here. Process number 1 is where the temperature changes. Do we understand this?
Yes, sir.
Process number 2 is the process where the state of the body changes. Do we understand this?
Yes, sir.
This is what you will write. And I'll give you a minute to note it down. Have you noted it down, bacha?
Yes, sir.
Then, sir, this thing, sir. And I will explain it to in brief. The heat given to a system of 1 gram, I have 1 gram of ice, for phase conversion, and I want to convert it into water. 1 gram of ice, I want to convert it into water. Whatever heat I require, it is known as latent heat of phase conversion. So it will be known as, if I have 1 gram of ice and I want to convert it into 1 gram of water, whatever heat I give it, that will be known as latent heat of melting. Do we understand this? Because ice melts into water. Do we understand this?
Yes, sir.
In this process, the heat given or heat lost, I always write heat as delta Q, is M. Where what is M here? Mass of the body. And what is L here? L is known as the latent heat of phase conversion. Do we understand this?
Yes, sir.
Please note it down. I'll give you more time to write this. You have this sheet with you. Do you have a sheet called calorimetry with you?
No, sir.
What sheet that we got? Which one do you got? You only got one sheet. Bad work done by whosoever had given you this. Anyways, you ask them that sir has sent us 6 sheets, 3 of theory and 3 of exercise. Give us all. Can you do that for me?
Sir.
Yes, sir. Then, sir, very good, sir. Have you noted it down, sir?
Last one, sir, please.
Okay, sir. I'll give you a minute, sir. A minute to win it.
Done, sir.
Done, sir. Then again, I'm showing you a part of the sheet. This is from the sheet of calorimetry. Specific heat. Specific heat is the heat that we had covered. Whenever a body gains or loses heat, the temperature rises or falls. Yes or no?
Yes, sir.
If delta Q is the amount of heat in this process, delta Q will be equal to M. What does M stand for here?
Mass.
What does S stand for here?
Heat.
What does delta theta stand for here?
Change in temperature.
Fatafat write it. From here to here, and then this formula. We understand this, everyone? I don't think you will have any doubts on this. Yes or no?
Yes, sir.
Please note it down, sir. This S is known as specific heat. I'll give you a minute to win it. Are we done, bacha?
No, sir.
No, sir. So much time, sir. Okay, sir. Take, sir.
Done, sir.
Done, sir. Then, sir, this thing, sir, again. This is just an elaboration of what is what. S is a constant which is known as specific heat of the body. We understand this, yes or no? Oops. S is a constant which is known as specific heat. Specific heat is delta Q divided by M into delta theta. Do we understand this?
Sir.
The SI unit is joule per kg Kelvin. CGS unit is calorie per gram per degree Celsius. Do we understand this? These are the values of specific heat of water. 4200 joule per kg or 1000 calorie per kg or 1 kilocalorie per kg or 1 calorie per gram degree Celsius. You must know this because you have just seen that a question comes and you will have to use one of these values. Yes or no?
Yes, sir.
Specific heat of steam is half the specific heat of water. You must know this, which is equal to the specific heat of ice. So specific heat of ice and steam both are equal and they are half the specific heat of water. I'll give you a minute to note down everything and you must remember this.
Done, sir.
Then sir, these things are a question, sir. Heat required to increases, not to increases, to increase the temperature of 1 kg of water by 20 degrees Celsius. You have to give me this answer. How much heat is required to raise the temperature of 1 kg of water by 20 degrees Celsius? I hope all of us are studying and not talking in the class. Please solve the question. Heat required to increase the temperature of 1 kg of water by 20 degrees Celsius. That is the question. Done, sir? Did you get the answer, sir?
210.
Yes, beta? 200?
210.
210. How did you get 10? I'm not sure. How did this have to be done? I hope I have attention of everyone in the class. Heat is ms into delta theta. Mass is 1 kg. 1 multiplied by specific heat capacity. I can write it as 1000 calorie per kg or 1 kilocalorie per kg. So I write it as 1 kilocalorie per kg. Multiplied by the change in temperature is 20. So my answer will be 20 kilocalorie. Do we understand this? Yes or no?
Yes, sir.
That was the answer that I was looking at. Do you all understand this? Can I have raise hand from all of you? Girls, are you there in the class? I hope there is the only reason that you are in the class is to study and not to do gossips. I don't like girls who gossip because that is one thing that you do when you have free time. And right now, what I understand is you don't have time. Isn't it?
Done, sir.
And sir, then, sir, some important points, sir, which you will note down, sir, and I'll give you enough time to note it down. Please better understand that we don't have time on our hands, and whatever time we have to utilize each and every second of it. I hope everyone understands this, the importance of time, and this is what we are going to use the importance of time with important points. And remember these points, every one of these points is plus 4 marks for you. We know that heat is ms divided by q delta q divided by m delta theta. If the substance undergoes change of state, remember when something is undergoing change of state, we cannot use this formula. Do we understand this? Because there is no change in temperature. Do we understand this?
Sir.
Then which formula do we use when there is change of state? We use the formula for latent heat. That will also come. Do we understand this?
Yes, sir.
So this change of state happens at constant temperature. Therefore, this heat becomes infinite or uncalculable. Thus, the specific heat of a substance when it melts or boils at constant temperature is infinite. Do we understand this?
Yes, sir.
If the temperature of the body changes without the transfer of heat, there is no transfer of heat. In that case, your specific heat would be zero. Do we understand this?
Sir.
Right now, I have water in this flask. I shake it. There is no transfer of heat, but the temperature of body will change. Temperature of the water inside will change. Do we understand this?
Yes, sir.
So the specific capacity of water which is inside this is zero. I'll give you a minute to note this down. If change in temperature is zero, specific heat is infinite. If heat is given is zero, specific heat is zero. These are the 2 points that you must remember. Can you remember it for me, bacha?
Definitely, sir.
Definitely, sir, that will help you a lot in scoring some great marks, some good marks. And that is the reason that we are doing so much of hard work. Coming and sitting in this heat. Understand? It's hard work. Please utilize it. I'll give you a minute to note this down. Have you noted it down?
No, sir.
Okay, I'll give you a minute.
Done, sir. Done, sir.
Okay, we have done this.
Yes, sir. Done, sir.
Then the next heading that we are going to do is known as heat capacity or thermal capacity. What we have done up till now is S. S is known as specific heat. Do we understand this?
Yes, sir.
So this heat capacity is nothing but M multiplied by S, and this is what you will just remember. Heat capacity or thermal capacity of a body is the mass of the body multiplied by the specific heat. Do we understand this?
Yes, sir.
Similarly, you have something known as water equivalent or W. Water equivalent of W or is equal to the specific heat capacity H, which is equal to mass into specific heat. Do we understand this?
Yes, sir.
So normally a question of water equivalent will not come, but if a question of water equivalent comes, you can assume that this water equivalent, whatever is given to you, is nothing but the specific heat capacity, is the thermal capacity of the body. Do we understand this?
Yes, sir.
Please note this down.
Done, sir.
Okay, you have done this.
Yes, sir.
Okay. Then you have this thing which is known as law of mixture. What happens when you mix two things? What will happen if you mix two things? For example, if you mix water at 50 degrees Celsius and water at 30 degrees Celsius. If you mix these two water, you might have used geyser in your home. Sometimes you want warm water, sometimes you want hotter water, sometimes you want colder water. So what do? You have a mixer, yes or no? You can mix hot water and cold water so that you can have an optimum temperature, yes or no?
Sir.
What happens in such a mixture? That is known as the law of mixture. When you when you mix two things at different temperatures, one is hotter, one is colder. The temperature that you have is somewhere in between the two temperatures, yes or no? Yes or no?
Yes, sir.
One of the body is hotter, one of the body is hotter, so that will lose some heat. Yes or no?
Yes, sir.
One of the body is colder, it will gain some heat. Yes or no?
Yes, sir.
Whatever heat once the hotter body has lost, the same heat colder body will gain. Yes or no?
Yes, sir.
That is known as the law of mixture, or you can also call it principle of calorimetry. You can call it principle of calorimetry. PLE, principle of calorimetry. Heat gained by one substance is equal to heat loss. Do we understand this?
Yes, sir.
So M1S1 into T1, temperature of the hotter body, minus Tm. Tm is the temperature of the mixture. Do we see this? That will be equal to M2S2 into Tm minus T2. From here, you can find out the value of this Tm, temperature of the mixture, and it will come at a very nice formula. The formula will be M1 S1 T1, temperature of 1, plus M2 S2 T2 divided by M1 S1 plus M2 S2. Do we understand this? This is the formula that you will note down. I'll give you a minute to notice. Everyone understands this? Can I have some raised hands? Well done, bacha. Please note it down. Have we done this, bacha?
Yes, sir.
Shall we move ahead? Shall I give you a question now?
Yes, sir.
This, sir, is the question, sir. If three different liquids of different masses, specific heat and temperature are mixed with each other, what is the temperature of the mixture at thermal equilibrium? M1, S1, T1 are mass, specific heat and temperature of liquid number 1. M2, S2, T2 are the values for liquid 2. This is for liquid 1. This is for liquid 2. This is for liquid 3. Can you tell me what will be the temperature of the mixture? Can you tell me what will be the temperature of the mixture? Your time starts now. You will have a minute to win it.
M- వచ్చింది వచ్చింది సార్
Did you get the answer, bacha?
ఎస్ సార్
What is the answer?
M1 S1 T1 plus
Just tell me what the answer.
M1 S1 T1 plus M2 S2 T2 plus M3 S3 T3 by M1 S1 plus M2 S2 plus M9.
Yes, that is the answer. Do we understand this? Girls, are we there in the class, or are we still thinking about it? Okay. Then we will just go through this, and we have already seen that what happens when the phase of the body changes, the temperature does not change. Yes or no? The state of the body changes. Yes or no? That heat is known as what? That heat is known as latent heat. Have you seen this? Yes or no?
Sir.
The formula is M into L. Yes or no?
Sir.
Latent heat of fusion. When solid melts into liquid or liquid freezes into solid, that is known as latent heat of fission. Please raise your hand that you understand this. Latent heat of vaporization is the heat to convert liquid into vapor, or latent heat of condensation is the heat to convert vapor into liquid. I'll give you 2 minutes to write this down. Latent heat of ice is 80 calories per gram. So 80 calories is required to melt ice into water at 0 degrees Celsius. Do we understand this?
Yes, sir.
Latent heat of steam is 540 calories per gram. That means 540 calories of heat is required to convert 1 gram of water at 100 degrees Celsius into steam at 100 degrees Celsius. I'll wind off the class here with this portion of phase change. In the next class, we will be dealing with more questions. Do we understand this? I'll give you a minute to note this down. If you have any doubt, please come up. Note it down. And the class from my side is over. So I'll keep this screen on. You note it down. I'll see you tomorrow. Tomorrow, your class will be of 2 hours from 9 to 11. So we'll be able to do more course in the same time. So I'll see you tomorrow. Take care and have a nice day.